What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, so today we're going to be taking a look at section 1.7, talking about linear independence. So in this section, we're going to take a look at how we can view the homogeneous equation ax equals 0. Remember, 0 refers to the 0 vector. We're going to view this in a different fashion. We're going to be able to use what we talked about previously to talk about linear independence. So we would say, by definition, an indexed set of vectors, those vectors are vectors v sub 1, v sub 2, so on and so forth, to v sub p, in a vector space Rn, is said to be linearly independent if the vector equation x sub 1 times vector v sub 1 plus x sub 2 times vector v sub 2 plus so on and so forth plus x sub p times vector v sub p is equal to 0, meaning the 0 vector here is equal to 0, has only the trivial solution. So that means the only way that I can assemble and add these vectors together with whatever coefficients I would like and get the 0 vector out, don't do that, would be if all of my coefficients were zeros. So x sub 1, x sub 2, so on and so forth to x sub p is 0. We would say that the same set is said to be linearly dependent if there does exist weights. We call them either x or we can call them c. I think c makes it feel a little bit more natural. If there do exist weights, c sub 1, c sub 2, so on and so forth to c sub p, where they're not all 0. Some of them could be 0, but the point is that not all of them have to be 0, such that that linear combination, c sub 1 times vector v sub 1 plus c sub 2 times vector v sub 2 plus so on and so forth plus c sub p times vector v sub p is equal to the 0 vector. And I don't want to try to overgeneralize this or give you something too colloquial to think about, but when I think about vectors being linearly independent, I think of them as being so dissimilar that the only way that I can combine them with coefficients and get 0 out, meaning the 0 vector, is if all of the coefficients happen to be 0. Whereas if I have a dependence relation, then the vectors, they're not super dissimilar, and there's some balancing that I can do, right? So there's some similarity between them. So I could maybe do 2 times a vector, and then -3 times another vector, and then 7 times another vector, and that balances everything out to give me the 0 vector. So when I think of linear independence, I think of vectors that are too dissimilar for me to be able to build a linear combination to give me the 0 vector without cheating, right? If all the coefficients are 0, if all of my scalar weights are 0, then of course everything's going to 0 out. But the question is really, is there any other way I can do it? Can I have non-trivial weights that give me the 0 vector? And if there's a bit of sort of back and forth, some sort of conversation between the vectors or some similarity there, then maybe I can do that and have some dependence relation. That's sort of an idea. Really, the thing that I want to focus on is that we can treat these as homogeneous matrix equations and get our answer that way. So we don't even have to, guess or stare at them too much. We would say the columns of a matrix A are linearly independent if and only if the equation ax equals 0, and again, that's the 0 vector, has only the trivial solution. And we'd say, if I'm just talking about 2 vectors, it's actually a very quick conversation. A set of 2 vectors, vectors v sub 1 and v sub 2, is linearly dependent if at least one of the vectors is a multiple of the other. The set is linearly independent if and only if neither of the vectors is a multiple of the other. So with a set of 2 vectors, it's actually kind of quick to determine whether or not they're an independent or a dependent set. But if we have more than that, then chances are we want to go through some row reduction. Let's take a look at this first question we have here. Determine if the following vectors are linearly dependent. Now here I have a set of 3 vectors, 0, 2, 3, 0, 0, -8, -1, 3, +1. And I think that you can look at this and get a sense as to what's happening by inspection. I think you can even argue it too. But the best way to go about this is to go through some row reduction. So what I'm going to do, what I'm going to encourage you to do, is I'm going to say make a matrix where these vectors are columns. So my first column is going to be 0, 2, 3. My next column is 0, 0, -8. And then my last column is -1, 3, 1. Now I want to reduce So let's go ahead and reduce. So I'm going to scale row 1. I'll do a negative row 1, just flipping the sign there. 0, 0, 1. And just for the sake of row reduction, I'm going to scale rows 2 and 3. I'm going to do 3 times row 2, and I'm going to do 2 times row 3. Just makes my row replacement a bit nicer. So here I'll say, okay, if I do 3 times everything in row 2, 3 times 2 gives me 6, and then 0 stays, and then 3 times 3 is 9. And then here, 2 times everything in row 3, 2 times 3 is going to give me 6. 2 times negative 8 is going to give me negative 16. And then 2 times 1 gives me 2. And now I can work through some row replacement. So I'm going to go ahead and I'm going to do, maybe row 3 minus row 2. And at some point I'm probably going to have to interchange some rows. But for now, I'm just having a good time. Yeah, it looks like I want to move these around. But if I do row 3 minus row 2, let me rewrite row 2. I get 6 minus 6 gives me a 0 that I had wanted. Negative 16 minus 0 gives me negative 16. And then 2 minus 9 gives me negative 7. So far so good. But now what I can do is I can go through and move the rows around and scale them. So here I would want to kind of swap in a bit of an awkward way. So for example, I would want row 1 to be at the bottom. And then I would want to put row 2 at the top. And then row 3 can go in the middle. So here at the top I'm going to have row 2, which is 6, 0, 9. And then here I can put the 0, negative 16, negative 7 in row 2, and then 0, 0, 1 in row 3. And aside from scaling, I have a really good looking column 1. And if I take a look at column 3, I have a really nice leading entry, but I want to get those zeros above it. So maybe let me do that next, because I can actually do that pretty nicely, kind of surgically. I can replace row 1 with row 1 minus 9 times row 3. And I can replace row 2 with row 2 plus 7 times row 3. And I'm going to rewrite row 3 just to start. But here in row 1, I get 6 minus 9 times 0 keeps my 6. 0 minus 9 times 0 gives me 0. 9 minus 9 times 1 gives me 0 that I wanted. And in row 2, 0 plus 7 times 0 keeps my 0. Negative 16 plus 7 times 0 keeps my negative 16 preserved. Negative 7 plus 7 times 1 gives me that 0 that I wanted. And now I can see up to scaling. So I would want to do, for example, a 1/6 row 1 and a negative 1 over 16 row 2. Up to scaling, I get everything reduces really nicely. First row is 1, 0, 0. Second row is 0, 1, 0. Sorry. Third row is 0, 0, 1. And I didn't bother augmenting this with the 0 vector. In fact, no operations on 0, no linear operations on 0 are going to change that. So even if I had included that along, or here just reducing this as a coefficient matrix, and now, for example, I can introduce this augmented part of it at no extra cost, it's perfectly fine. Keep in mind, if I'm augmenting with something that is not the 0 vector, I can't do this because I need to know how the operations affect it. But since I'm only working with zeros in this column, any linear combination of zeros is just going to give me more zeros. So I get no sort of ill effect adding this now. But what is this telling me? It's giving me my weights. It says first weight, call it x sub 1 or call it c sub 1, whatever you want. The c sub 1 is 0. My second weight, c sub 2, is 0. And my third weight, c sub 3, is 0. And this is the only solution I have. I have no free variable. I have no non-trivial solution. So we maybe note this only the trivial solution. And what this means for us is that we have a set of vectors that are linearly independent. So this means we have a linearly independent set of vectors. Maybe that's what we were sort of guessing looking at this. So always a good idea to do the row reduction. However, in this next example, and you can see I don't have a lot of space for it, but there's a reason why, I want to determine if the following vectors are linearly dependent. Since I just have 2 vectors, I can still go through row reduction, no harm in doing that. But really all I have to look for is to check to see if the vectors are multiples of each other. And if I look here, I'd say, okay, to get from negative 1 to negative 3, I'd have to multiply by 3. So here, let me actually write these. I'll call this first vector u, the second vector v. We would say, well, what about 3 times vector u? That's going to give me 3 times this vector negative 1, 3. which is going to give me a first entry of -3, which looks good, so check. But then 3 times 3 gives me +9, not -9. And in fact, we can probably see right away by inspection that the signs that we have aren't going to be conducive to these being multiples of each other. Because to preserve the sign of the first entry, I'd multiply by something positive, namely 3. But to change the sign of the second entry, now that scalar weight has to actually be negative to flip the sign. Well, that's not going to work, right? It's not going to work. So this means the vectors are not multiples of each other, almost disguised as, but are not. Vectors are not multiples of each other. And this means we have a linearly independent set. So we could say they are linearly independent. Right? If they were multiples of each other, they would be dependent. We have that sort of written up here. Right? Linearly dependent if one of the vectors is a multiple of the other. Not the case, not the case. And it's one or the other, right? They're either independent or dependent. So if it's not this, then it's that. If it's not that, then it's this. What about here? Determine if the columns of the matrix form a linearly independent set. So this is already built to me as a matrix. I want to think about these columns as the vectors, but I can go ahead and start reducing. Now, I would go ahead and probably, for example, move some of these things around. So let me do a row interchange. Let me switch rows 3 and 1. So my very top row is going to be this 1, 1, minus 5. Second row, I'm going to leave that the same, 0, negative 1, 5. Then my third row is going to be this -4, -3, 0. And I'm going to leave that bottom row as 2, 1, negative 10. Now from here, I can go through some row reduction, right? I can use this 1 in the upper left corner, which is why I switch these around. I want a 1 in that upper left corner to start the process. So no harm now. Looks good. And then I can, row 2 looks fine. So I'll sort of leave row 2 out of it. But in row 3, I'm going to replace with row 3 plus 4 times row 1. And row 4, I'm going to replace with row 4 minus 2 row 1. So let's see what I get for row 3. I'm going to get -4 plus 4 times 1 gives me that 0 that I wanted. I'm leaving space for row 2. We'll talk about that later. And then I have -3 plus 4 times 1. -3 plus 4 gives me +1. And then 0 plus 4 times -5. That's going to give me 0 plus -20 gives me -20. And in row 4's position, I'm going to get 2 minus 2 times 1 gives me that 0 that I had wanted. 1 minus 2 times 1, or that's 1 minus 2, gives me -1. And then -10 minus 2 times -5, so that's -10 plus 10, is going to give me 0. And the reason why I didn't write row 2 yet, you can just rewrite it as it is, and either in the next step, or I'm going to do it in this step since I didn't really do anything with it otherwise, I'm just going to scale it. I'm going to flip its sign. I want that leading entry to be a +1, so I'm going to just flip the sign on it. So I'm going to replace row 2 with a negative row 2. Either now or in the next step, I'll do it now. So 0, +1, -5. So it looks really good so far. Now I can reduce further. So if I actually take a look at, and it's kind of hard to ignore the human aspect here, there is a row reduction algorithm that we could, follow that's outlined very rigorously in the text. I don't think it's worth your while. I think it's important to know how you should approach row reduction, but seeing something like this right away, I'm already thinking about some heavy row reduction in row 1 using row 2. And there's no reason why I shouldn't do that. So let's do it. So I would go ahead and I would replace row 1 with row 1 minus row 2. And nothing will be more satisfying because 1 minus 0 gives me 1, but then 1 minus 1 gives me 0, -5 minus -5 gives me 0, and that I think is great. And I'm going to rewrite all the rest of this stuff. But another thing that I'm considering doing is perhaps scaling row 4 I can just do that now. We'll flip the sign on row 4. Negative row 4 gives me 0, 1, 0. And now this row 4 doesn't look like it really wants to be row 4. Looks like that kind of wants to maybe be row 2. So I'm not going to say no to that. We'll do a little swapperoo. We'll put row 4 in row 2's position, row 2 at the bottom. Seems fair. And I'll keep row 1 the same. Row 2 is going to be that 0, 1, 0. Looks good. Row 3 is going to stay 0, 1, negative 20. And then down in row 4's position, 0, 1, negative 5. And I want to row reduce. Now that first column looks great. If I take a look at my second column, I can use that leading 1 in row 2's second position to get zeros underneath. And that's what I'm trying to do. So we're going to do it. So I can replace row 3 with row 3 minus row 2, and I can replace row 4 with row 4 minus row 2. Rewrite rows 1 and 2. But here at row 3's position, I get 0 minus 0 gives me 0, 1 minus 1 gives me 0, and negative 20 minus 0 gives me negative 20. And in row 4's position, 0 minus 0 gives me 0, 1 minus 1 gives me 0, and negative 5 minus 0 gives me negative 5. Now I want you to notice that from here I can actually scale rows 3 and 4. So we'll do a negative 1 over 20 row 3, a negative 1/5 row 4. I can rewrite rows 1 and 2. And then those rows become 0, 0, 1, both of them. And I can actually then eliminate row 4 with a very quick row reduction. So I would say, yeah, let's replace row 4 with row 4 minus row 3. And it looks like we have our answer. 0 minus 0 gives me 0, and then again, 1 minus 1 gives me 0. Now keep in mind, I haven't been augmenting this, but if I wanted to augment, now I could certainly do that. Since I'm thinking about a homogeneous matrix equation, any of those operations on zeros would have just churned out more zeros. So whether or not I'm showing that work as I'm going or introducing it at the tail end shouldn't make a difference. And this is telling me very specifically C sub 1 is 0. C sub 2 is 0. C sub 3 is 0. And I have an extra row with no useful information, but not a false statement. Everything is consistent here. Just saying 0 equals 0, which is, hey, that's great to know. Thank you for telling me. But this is the info that I want. This is saying, hey, the only scalar weights you're going to get on these column vectors, think about these vectors as column vectors now, have to be weights of 0. So this means all weights must be 0. So then I have a linearly independent set. Linearly independent set. If I want to be careful of vectors formed by the columns of matrix A. Did I call this matrix A? Nope, I'm going to name it matrix A right now. Bam. So we saw a lot of examples of things that are linearly independent. Let's take a look at another example, see what we get for this one. I want to determine if the columns of the matrix form a linearly independent set. Now again, I can start row reducing. So let me go ahead and do that. Let me actually start by scaling row 2. I think that's not a bad move. Everything is divisible by 2. I want to maybe consider flipping the sign as well. So let me replace row 2 with a negative 1/2 row 2. I can rewrite row 1. That's 1, negative 2, 3, 2. Row 2, think about cutting everything in half, but also flipping the sign. So I'm going to get positive 1. I'm going to get negative 2. I'm going to get positive 3. I'm going to get negative 1. And then I can rewrite row 3. Row 3 is just at the bottom there. It looks like I can get quite a bit of reduction done. So now I can replace row 2 with row 2 minus row 1. Row 1 I'm just going to rewrite. And if you're wondering, there's a lot of row reduction in the course, so I'm doing it. You should be doing it too. I get 1 minus 1 gives me 0. Negative 2 minus negative 2 gives me 0. 3 minus 3 gives me 0. 1 minus negative 2 gives me negative 3. Or sorry, negative 1 minus 2 gives me negative 3. Negative 1 minus 2 gives me negative 3. And then I can rewrite row 3. Yes. Now, a couple things I want to consider here. I want to think about interchanging rows 2 and 3. I want to think about scaling row 3 as well. Let me swap them first. So row 1, just going to leave it alone, rewrite it. My new row 2 is going to be that 0, 1, 1, 3. And then here, my row at the bottom is going to be 0, 0, 0, negative 3, which I will scale that now. So we'll replace row 3 with a negative 1/3 row 3. Gives me 0, 0, 0, 1. And what's nice about that row at the bottom is I can very safely and surgically eliminate the entries above it. Right, since any operation utilizing this 0 here is going to preserve in the row replacement, it's really just where that leading entry is that's going to give me the zeros above it. So I'm telling you, and I'd place money on this, that I bet I can do a row replacement to pick off this 2 at the end of row 1 and to pick off this 3 at the end of row 2. Let me know if you want to take that bet. But let's go ahead and replace row 1 with row 1 minus 2 row 3. I'm also going to want to think about replacing row 2 with row 2 minus 3 row 3. Let me rewrite row 3 just so I don't have to worry about that later. But here I'm going to get 1 minus 2 times 0 keeps my 1. Negative 2 minus 2 times 0 keeps my negative 2. 3 minus 2 times 0 keeps my 3. But 2 minus 2 times 1 gives me that 0 that I had wanted. And similarly here in row 2, 0 minus 3 times 0 gives me 0. 1 minus 3 times 0 keeps my 1. And then again. But 3 minus 3 times 1 gives me that 0 that I wanted. So it looks really good. But I've sort of been neglecting working with this leading entry right here in row 2. I got a 0 beneath it, but I got to get that 0 above it. So that negative 2 has to go. And whatever else happens alongside that is just what's going to have to happen. So I would say let's go to row 1. Let's do it. And replace row 1 with row 1 plus 2 times row 2. So what's that going to give me? 1 plus 2 times 0 keeps my 1. Negative 2 plus 2 times 1 gives me 0. 3 plus 2 times 1, 3 plus 2 gives me 5. And 0 plus 2 times 0 gives me 0. And I can rewrite the rest of the rows. Now always check those leading entries, check their columns. Here's my leading entry. The column looks beautiful otherwise. I want the leading one to be the only non-zero entry in its column. Go into row 2, go in the left, pass through any zeros. There's my leading entry. Its column looks beautiful. Row 3 is the last row to check. Pass through the zeros. There's my leading entry. It's a leading one, which is good. Only non-zero entry in its column. We're fully reduced then. Fully reduced. Fully reduced row echelon form. But what is this telling me? Well, here this first row is saying 1c sub 1, and you can use x's if you like, plus 5c sub 3. And then if I was thinking about augmenting this, and that's really what I want to maybe consider is augmenting this with a column of zeros, is equal to 0. This is c sub 3 here. The second row is saying 1c sub 2 plus 1c sub 3 is equal to 0. And then the fourth row is saying 0c1, 0c2, 0c3. It's saying 1c sub 4 equals 0. So it's saying c sub 4 is equal to 0. And important, definitely worthwhile to point out that since my third column is the only column that is not a pivot column, this is where my free variable lives, which means that c sub 3 is my free variable. So what do we want to do? Well, we want to consider building a parametric vector description of our solution. So if I solve for the basic variables, we'd say, well, c sub 1 is equal to negative 5c sub 3. C sub 2 is equal to negative c sub 3. C sub 3, of course, is starring as itself in the production. So c sub 3 is c sub 3. And c sub 4 is 0, but I, of course, can write that as 0 times c sub 3 at no extra cost. And how is this going to look in general as a parametric vector description? I could call this vector x and say, well, if I just bring out c sub 3 as a scalar weight, I'm left behind with the coefficients, -5, -1, +1 for that free variable to survive, and then 0. And this is my parametric vector form of my solution. But this means something a little bit specialer to us, since we're talking about linear dependence and linear independence, and we can actually check our work a bit. So what's nice about this is now I can actually build a non-trivial vector. And there's a trick to this. The trick is don't pick 0. If I pick c sub 3 to be 0, it's going to kill all of these entries off, and it's going to give me the illusion that I have linearly independent vectors. That's not the case. That's not the case here. What this is showing, since I have a free variable, this means I have a non-trivial solution. Which means we do have linear dependence. And I can actually build the dependency relationship. So pick whatever you want for c sub 3. Don't pick 0. You could pick 1, and that'll give you the vector -5, -1, 1, 0. I think negative numbers have a weird connotation to them, so I might pick something like -1. So let me change colors too. I want everything to stand out real nice for y'all. So if I let c sub 3 be -1, say let, you could pick something different, don't pick 0. Then the vector that I get, multiplying -1 to all of these entries, is +5, +1, -1, 0. But this is trying to tell me what coefficients I should have on the vectors. Let me sort of get some space for this. So I'm saying 5 times a vector plus 1 times a vector plus -1 times a vector plus 0 times a vector. And I'm hoping that this linear combination gives me the 0 vector out. But let's see if that's what happens. What were my vectors? Those were the columns of this matrix. So 1, -2, 0 was the first. Do you have to check? No. If you're feeling comfortable and confident with what we're talking about, you can just assume you did the work correctly, but it's nice to check. So -2, 4, 1 was the next vector. What was the third vector? 3, -6, 1. What was this one? 2, 2, 3? Well, got to go back and check that because I don't have a great memory. But I think it was 2, 2, 3 when I glanced at it. 2, 2, 3. And I want to know, hey, did it work? Did I find a non-trivial linear combination? Did I find non-trivial weights? Let's check. If I go through the arithmetic, take a look at the top entries. 5 minus 2 gives me 3. Minus 3 gives me 0. And then a 0 gives me 0. So check. What about here? -10 plus 4 plus 6 plus 0. 4 and 6 give me 10. Minus 10 gives me 0. Hey, looks good. 0, 1, -1, 0, give me 0. So I have, and I can build many of these, infinitely many of these. I can just change what I choose for c sub 3, don't pick 0, and I can show you different weights that are going to allow a linear combination on these vectors. These are the 4 columns of my matrix, column v sub 1, v sub 2, v sub 3, and v sub 4. And I've solved for values for c sub 1, c sub 2, c sub 3, and c sub 4 that give me the 0 vector out. And not all of these weights are 0. Not all of them are 0. One of them is, but not all of them are. So it worked. We have proof. Let's take a look at this example now. And here we're sort of talking about something we discussed earlier on, along with some new topic for us. I want to know for what value of h is vector v3 in the span of v1 and v2. Now, in order to answer this question, remember what we have to do. We want to take vectors v1 and v2 as columns and augment that with vector v3 and try to solve for what h would be. And notice this third vector v3 has mention of h in it, or we don't know what h is, some constant, right? So I can actually set that up, making my first column 1, -3, -5, my second column -3, 9, 15, and then augmenting with vector v3 with entries 2, -5h. And I would like to row reduce this. So we'll say, okay, let's row reduce. So what I can do is I can work in row 2. So let me rewrite row 1. And this is not a homogeneous system. Notice I'm augmenting with things that aren't zeros. But I can work in row 2, replacing row 2 with row 2 plus 3 times row 1. So -3 plus 3 gives me 0. 9 plus 3 times -3, that's 9 plus -9 gives me 0. And -5 plus 3 times 2, -5 plus 6 is going to give me 1. And I can rewrite row 3. But I want you to notice something about this right away. The second row that we have gives me something that's inconsistent. That row is saying, 0 C1 plus 0 C2 equals 1, or is really saying 0 equals 1, which makes me feel like this. Not true. It's a false statement. So what this is telling me, it's answering the question for me. I was trying to find a value for h that allows this third vector to be in the span of vectors v1 and v2. Right away setting that up, I get something that's inconsistent. There's no solution, which means, and I need to interpret this as, there is no value for h that will allow this to happen. So we'll say there is no value for h where v3 is in the span of v1 and v2. I set out to find a suitable value, and hey, everything got derailed. The system was inconsistent. No good. Can't happen. Not gonna happen. Not today. But what about this next question? This is a different question. It needs a different setup, a different consideration. Want to know for what value of h is v1, v2, and v3, the set of all three vectors, linearly dependent? And this one we would set up very similar to what we were doing already. So now what I can do is I can actually just build a coefficient matrix with these three vectors. So my first column is going to be 1, -3, -5. My second column is -3, 9, 15. My third column is 2, -5h. And then I want to row reduce. Now there is a way that we can solve this much quicker, but let me show you the way that has some nice corroborative work. And I'll just go through the row reduction as it would normally. I would start with the same operation as well. I would do row 2 plus 3 times row 1 in row 2's position. And this is not augmented. If I'm thinking about augmenting it, I'm augmenting it with the 0 vector. This is a homogeneous system now. But I get -3 plus 3 gives me 0. 9 plus -9 gives me 0. And we said -5 plus 3 times 2, -5 plus 6 gives me 1. And then from there, I can just, rewrite row 3. I'm going to work with row 3 eventually. But since it has this delicate value h in it, I might sort of wait and see what else I can do before doing that. But you can jump in and work with it whenever you feel comfortable. Now what I would do is I would replace row 1 with row 1 minus 2 row 2. I can use this 1 in row 2's third entry to get rid of that entry above it. So I get 1 minus 2 times 0 gives me 1. -3 minus 2 times 0 gives me -3. And then 2 minus 2 gives me 0. So this is looking very reduced. And now, can't avoid it forever, but I should consider working in row 3. There's really nothing to be afraid of. We're all here together. We'll, stick together. I'm going to replace row 3 with row 3 plus 5 times row 1. Let me rewrite rows 1 and 2. And remember, I'm augmenting this with the 0 vector. I just don't have to necessarily show that to get through the work. You can, though. -5 plus 5 times 1 gives me 0. 15 plus 5 times negative 3, that's 15 plus negative 15, gives me 0. And h plus 5 times 0 gives me h. Now what's cool about this is I can actually think about some different considerations on h. If h happens to be 0, then this row of all zeros immediately gives me nothing of any real consideration and gives me a free variable. However, let's say h isn't 0, right? If it is 0, then it's great. My free variable's there. We have some dependency relation. If it's non-zero, then in theory I would go ahead and scale it, and I would turn it into a 1, and then I'd be able to eliminate it. So some sort of, and this depends on what h is. If it's 0 already, I wouldn't bother doing this, but if it's non-zero, then I could work with, for example, row 3 minus h row 2, sort of a funny way to consider the operation. But we'd say, okay, so this gives me the row of all zeros anyways. And if I consider augmenting this now with my zeros, now that I'm all done reducing, we can actually see a dependency relation. So here we'd say that first row is saying c sub 1 minus 3 c sub 2 equals 0. And the next row is saying c sub 3 equals 0. And this really means that c sub 2 is our free variable. And if I want to build a parametric vector description of this solution, we say, well, x is equal to c sub 2 times the vector. Here, if I think about moving this over, it'd be 3 c sub 2. Here, c sub 2 is itself, so I'll give a 1 there for the free variable. C sub 3 is 0, c sub 2. So I'm able to get this vector, and we can actually then build out our coefficients. So if I let c sub 2 be 1, then I get this vector 3, 1, 0. Remember, don't let the free variable be 0. It's going to ruin all that you worked for. But this gives me now a dependency relation. So we're saying 3 times the first column plus 1 times the second column plus 0 times the third column is equal to, and hopefully this is equal to the 0 vector. That's why I'm doing all of this work. But let's see if it did what we thought it did. So okay, so that first row, or the first column is 1, negative 3, negative 5. Second column, my second vector, negative 3, 9, 15. My third column was 2, negative 5h. And I'm hoping this gives me the 0 vector out. Does it? Let's check. 3 minus 3 plus 0 is 0. Negative 9 plus 9 plus 0 is 0. Negative 15 plus 15 plus 0 is 0. So it works. But there's actually something special to consider here then. Since we're zeroing out this third vector, right, that one happens to have a 0 coefficient, but not all coefficients are 0, means that it doesn't matter what h is. So here we get linear dependence no matter what h is. So any value for h allows linear dependence. There's a faster way to solve this one with a less satisfying argument, or maybe more satisfying depending on what you prefer. If you can notice right away that v1 and v2 are already multiples of each other. Negative 3 times v1 produces vector v2, then we already have a dependency relation that doesn't even take into account this third vector. So the dependency relation is already there, which means that literally anything could happen with this third vector. H can be anything it would want, and there's still a dependency relation, since that dependency relation is right there between the first two vectors. And if you're lucky enough to spot that, you could actually save yourself all this work here. But I think it's good to do this. This actually shows things in a bit more of a specific light. But a consideration I want to talk about. Let's take a look at this next one. Find the values of h for which the vectors are linearly dependent. This is another one that I think you can solve by inspection. Let's solve it by inspection first, and then let's see if we can corroborate it with some work. if you notice looking at these vectors, and if you stare at them for a while, that the first and the third vectors look eerily similar, we'd say, well, 2 to -2, -2 to +2, 4 to h. H should really be -4. And if h was -4, then I'd have that dependency relation. But what if I didn't know that? What if I was just row reducing, trying to be the best version of myself that I can be? Let's see if I have room to show this to justify it. I would go ahead and maybe scale rows 1 and 2. So we'll do a 1/2 row 1. I'll do a -1/2 row 2. So 1, 2, -1. Row 2 is going to be 1, 3, -1, and then 4, 7, h. And then I'll row reduce. So here I'm going to replace row 2 with row 2 minus row 1. And I can also consider replacing row 3 with row 3 minus 4 times row 1. So I'm going to rewrite row 1. Row 2's position, I get 1 minus 1 gives me 0. 3 minus 2 gives me 1. And -1 minus -1 gives me 0. Working in row 3, I get 4 minus 4 times 1 gives me 0. 7 minus 4 times 2, that's 7 minus 8 gives me -1. And h minus 4 times -1, that's h plus 4. I don't know what that is, so I have to just write it as h plus 4 right in there for that entry. Now what I can do from there is I can actually use row 2 to eliminate above and beneath it, the 2 and the -1. So I'll say, well, let's go ahead and replace row 1 with row 1 minus 2 row 2, and replace row 3 with row 3 plus row 2. I'm going to rewrite row 2 to start, right in the middle. But then in row 1's position, I get 1 minus 2 times 0 is 1, 2 minus 2 times 1 is 0, -1 minus 2 times 0 is -1. And then here in row 3's position, we would say, okay, 0 plus 0 gives me 0, -1 plus 1 gives me 0, and then h plus 4 plus 0 gives me h plus 4 back. Now from here the question is, what do I want? What do I want? I want the vectors to be linearly dependent. For these vectors to be linearly dependent, and you can think about augmenting this with the 0 vector, for it to be dependent, I want a free variable. To have a free variable, I need to make sure that this entry is a 0. If this h plus 4 isn't a 0, it would be some non-zero value. I would scale it. It would give me a pivot entry. I could eliminate everything above it. I'm looking at you, -1. And I would have only a trivial solution. But I don't want that to happen. I want to explore the possibility, is there a non-trivial solution? There can be. That would mean that I would need a free variable. To have a free variable, I would need this third row to be a row of all zeros. For this third row to be a row of all zeros, I'll do this in a different color. So let me say, to have a free variable, I need row 3 to be a row of all zeros, which means that this particular entry right here, if I can sort of highlight it, h plus 4 must be 0, which means in turn that h has to be -4. That is the possibility. So that's what we said at the beginning, sort of by inspection, and it wasn't just the only answer by happenstance. It is the only answer corroborated now with our work. H would have to be -4. Then we have that dependency relation. Otherwise, we're not going to get the dependency relation. What about here? I got another very similar example. I want to know for what values of h are the vectors linearly dependent. Let's see if we can do this one. Hey, set it up. Set it up. Set it up. I'm just using these as columns. I'm sort of looking at it like it's a matrix already, if I'm being honest about what I'm doing. Just building the matrix. Now I want to reduce. Get used to it, right? You could scale. I'm just going to jump right into it. Let me rewrite row 1. It's got that 1 in the upper left corner already, which means I can replace row 2 with row 2 plus 2 times row 1. I can replace row 3 with row 3 plus 4 times row 1. What's this going to look like? I get negative 2 plus 2 gives me 0. 7 plus negative 6 gives me 1. 1 plus 2 times 2, or that's 1 plus 4, gives me 5. And then working in row 3's entries, negative 4 plus 4 gives me 0. 6 plus 4 times negative 3, so that's 6 plus negative 12 is going to give me negative 6. And then here I'm going to get h plus 4 times 2, or that's h plus 8. So there we go. Now I want to go ahead and keep reducing. This first column looks great. It looks like this second column is far from great, but I can actually work with this 1 in the second entry of the second row. I can get that 0 above it. I want to get a 0 beneath it as well, but let me maybe actually start, just see what happens with row 1. Otherwise it can get kind of messy. Maybe it's going to have to, but let me see if I can avoid that. I'm going to replace row 1 with row 1 plus 3 times row 2. So I get 1 plus 3 times 0 gives me 1. Negative 3 plus 3 times 1 gives me that 0 that I wanted. 2 plus 3 times 5. So that's 2 plus 15 gives me 17. And then I can rewrite row 2. And here I can rewrite row 3. Now it looks like I can't really go much further without doing some operations in row 3. So hey, we said we were willing to do it. Let's do it. I'm going to replace row 3 with row 3 plus 6 times row 2. You rewrite rows 1 and 2. I get 0 plus 6 times 0 gives me 0. Negative 6 plus 6 times 1 gives me that 0 that I wanted. And then I have h plus 8 plus 6 times 5. So h plus 8 plus 6 times 5 is going to give me 30. So all right, it's really h plus 38, certainly, but you know what we're doing. And then I want to think about augmenting this with a column of zeros. And we can make a similar comment to what we made before. We can say, well, in order for this to give me some dependency relation, I need this last row to be a row of all zeros. If this entry isn't a 0 here, then it is a pivot entry. I can scale it, make it a leading 1. I can eliminate everything above it very safely and surgically. Now I only have the trivial solution. I've failed in my journey to get dependence relations. But if this happens to be a 0, if I have this row of all zeros, then I have a free variable. So to have linear dependence, we need, and it looks weird to write h plus 8 plus 30, that's really h plus 38. I need that entry h plus 38 to be 0, which means that h would have to be equal to negative 38. And that's the value for h that's going to give me linear dependence. So for what values of h do we get linear dependence? H has got to be negative 38. Let's take a look at just a little bit more. Let's see if we can determine by inspection whether the vectors that we have are linearly independent. Remember, if I just have two vectors, it's going to be quick. I want to know, are they multiples of each other? I look at these vectors, 2, negative 4, 8, negative 3, 6, negative 12. It looks close. I sort of suspect something. So let me call these vectors u and v. What if I took vector u and multiplied it by a negative 3 halves? I want to know, what is this going to produce? Well, okay, so that's negative 3 halves times this vector 2, negative 4, 8. What's that going to give me? Well, 2 divided by 2 cancels, and I get negative 3 for the first entry. So far, so good. Here the signs resolve. 4 divided by 2 gives me 2. 2 times 3 gives me 6, and that's positive. And for this last entry, 8 divided by 2 gives me 4. 4 times negative 3 gives me negative 12. And this is identically vector v. So we actually have this relation that negative 3 halves times vector u is equal to vector v. Or you could go in the opposite direction and show it that way, perfectly fine. But this means they are multiples of each other. So the vectors are multiples of each other, which means we have linear dependence. So we can say, let's say they are linearly dependent. What about this next set here? Determined by inspection if the set is linearly independent. Negative 8, positive 12, negative 4, 2, negative 3, negative 1. Well, I notice something right away that's kind of frustrating. If I divide the first vector's entries by a negative 4, it's almost going to work. But the problem is this very last entry, the signs are a bit messed up. So we'd say, okay, negative 8 divided by negative 4 gives me positive 2. 12 divided by negative 4 gives me negative 3. But negative 4 divided by negative 4 should be a positive 1. And something I can always check for first if I have something interesting going on with the signs is just to make sure that the signs are preserved, either staying exactly the same or flipping exactly the opposite for each entry. And if that doesn't quite happen perfectly, then I know it's going to fail. So in this case, the signs are messed up. I think it might be even nice to say almost. All right, I see what you're trying to do here. If I call these vectors u and v, we'd say negative 1/4 times vector u does not equal vector v, but almost, in which case I have linear independence. So the vectors are linearly independent. We'd say these are not multiples of each other. What about this last set here? Determined by inspection whether the vectors are linearly independent. Much more difficult when we don't have just two vectors, but there's something very special happening here in this case. I have three vectors, but one of my vectors, right away I'm noticing, is the 0 vector. And there's a little bit of kind of a workaround, almost feels like a cheat or like a math hack that we can do here. Let me call these vectors, let me call them v1, v2, and v3 to sort of coincide with our definitions and theorems in our lecture a bit better. But since one of the vectors already has all 0 entries, that's going to be my sort of get out of jail free card. Because what I can do, and let me know in the comments below if you think this is an illegal move. It's not technically, but it feels that way maybe. Is I can do 0 times vector v sub 1 plus 0 times vector v sub 2 plus, it could be anything really. So I'm going to say k times vector v sub 3, in particular where k does not equal 0. So it could be 2, it could be 1, it could be negative 7. And that's going to produce the 0 vector for me. So I can give a specific example of this, so it's not so generic. But we could say, 0 times vector v sub 1 plus 0 times vector v sub 2 plus 1 times vector v sub 3 is going to give me the 0 vector out. We'd say, well, hold on a second. Of course, the coefficient on vector v sub 3 in the linear combination doesn't matter. All the entries are 0 anyways. But by definition, all I need is a linear combination where not all, looking at you, not all coefficients are 0. Some of them can be zeros. In fact, most of them can be zeros. But as long as somewhere in the coefficients I have something that is not 0 as a coefficient, this is really a 1 here, so 1 times v3, then that means I have a dependency relation. So these vectors, this set, is linearly dependent. It's an unenthusiastic linear dependence, right? It feels like we're kind of cheating the system, but we do get linear dependence. And that's something to think about and to spot. If you ever have a set of vectors where one of the vectors is the 0 vector, hey, remember that we have this talk. Speaking of which, we have some theorems to close out with. Let's just go through them quickly. Characterization of linearly dependent sets, an indexed set capital S of vectors v1 through vp of 2 or more vectors is linearly dependent if and only if at least one of the vectors in the set S is a linear combination of the others. In fact, if S is linearly dependent and the first vector is not the 0 vector, then some vector in that set v sub j with j greater than 1 is a linear combination of the preceding vectors. And that's v sub 1 through v sub j minus 1. And I have a bit of a disclaimer here. Be careful to notice this theorem does not say that every vector in a linearly dependent set is a linear combination of the preceding vectors. A vector in a linearly dependent set may fail to be a linear combination of the other vectors. But we're just able to get some dependency relation. Another nice theorem, useful to discuss, if a set contains more vectors than there are entries in each vector, then the set is automatically linearly dependent. So for example, if I have vectors with 3 entries in them, and I have 7 vectors with 3 entries in them, I can tell right away I have too many vectors with not enough entries. Right away we should know that we have a linearly dependent set. So we say any set of vectors v1 through vp in vector space Rn is going to be a dependent set if p, the number of vectors that I have in the subscripts, is greater than n, the vector space that they're living in. You think, if I have 4 vectors in R2, they can't all be independent, right? At most I can get 2 of them to be independent, but no more than that. And this one, which we just talked about, if a set capital S of vectors v sub 1 through v sub p in vector space Rn contains the 0 vector, then the set is linearly dependent automatically, right? We get that result. Hey, I hope you enjoyed the content. I hope you're doing well wherever you are. No matter what, I want to make sure that you're going to promise me that you will keep learning, keep dreaming, and always follow your heart. I'm not going anywhere. We're going to be doing more math soon. So just, rest up, do what you got to do, and we'll be back in it to win it shortly. But until then, make sure that you take care, and I will see you next time.